Hello and welcome. Tonight, we'll be exploring 10 of the most terrifying entities and theoretical phenomena the universe has to offer. When most people imagine fear, they think of predators hiding in the dark, towering storms rolling across the horizon, or creatures born from myths and nightmares. For thousands of years, those were the dangers our ancestors learned to recognize. They had shapes, sounds, and intentions. They could be seen, heard, or escaped. But the universe tells a very different story. Out there, beyond the comforting blue sky that has sheltered every generation of humanity, fear rarely arrives with claws or glowing eyes. Instead, it appears as silence that stretches for billions of miles, gravity so powerful that it bends time itself, invisible forces that quietly guide entire galaxies, and ideas so strange that they challenge the very meaning of reality. Some of these phenomena have already been observed through telescopes and spacecraft. Others remain theoretical, emerging from equations that describe nature with astonishing precision. Yet, whether they have been directly witnessed or still exist only as possibilities, each one reveals something profound about the cosmos we inhabit. Together, they remind us that the universe is far more mysterious and far more extraordinary than our everyday lives might suggest. Perhaps that is what makes these ideas so captivating. The deeper we explore the universe, the less it resembles an empty stage filled with distant stars. Instead, it begins to feel like a vast, intricate landscape shaped by laws that have been unfolding for nearly 14 billion years. Those laws are neither cruel nor compassionate. They do not pause for civilizations, dreams, or memories. They simply continue, with remarkable patience and unwavering consistency. At first, that realization may sound unsettling. Yet there is another way to look at it. In understanding the immense forces that govern the cosmos, we also begin to understand our own place within it. The stars above us, the atoms within us, and even the quiet rhythm of time itself, all belong to the same remarkable story. The universe is not trying to frighten us. It is simply revealing how much larger reality truly is than the world we experience each day. Throughout this journey, we won't rush from one astonishing discovery to the next. Instead, we'll move slowly, allowing each idea to unfold with the same quiet patience that shaped the cosmos itself. Along the way, we'll translate complex science into gentle images, familiar comparisons, and simple observations, making even the strangest concepts feel a little closer to home. And as our understanding gradually expands, something unexpected may happen. The greatest source of wonder is no longer the terrifying objects scattered across the universe. It is the realization that the universe has never needed monsters to inspire awe. So, find a comfortable place to rest, settle into a quiet moment, and let your thoughts drift gently upward toward the night sky. Our journey begins not with the largest black hole or the brightest explosion ever observed. It begins with something much quieter. It begins with what happens when every familiar sign of home quietly disappears, leaving only you and the infinite silence beyond. Imagine, for just a moment, that you open your eyes and discover there is no longer a world beneath your feet. No ground welcomes your next step. No horizon separates the land from the sky. There is no breeze against your skin, no distant birdsong, no quiet rustling of leaves. Even the comforting pull of gravity, something you have trusted every second of your life without ever noticing it, has quietly disappeared. Instead, you find yourself suspended within an endless ocean of darkness. At first, it might seem peaceful. The stars are still there, scattered across the blackness like tiny lanterns hung impossibly far apart. They shimmer with the same quiet beauty they have always possessed. Nothing appears to be chasing you. Nothing seems violent. The universe looks almost perfectly calm. Yet within a few moments, something begins to feel deeply unsettling. Your mind searches instinctively for direction. Which way is up? Which way is down? Where should you go? On Earth, these questions are so simple that we rarely think about them. Gravity quietly answers them every moment of our lives. Mountains stand above us. Oceans lie below us. Buildings, trees, and clouds constantly remind our brains where we are. Out here, every one of those invisible guides has vanished. The universe offers no preferred direction. You could slowly turn in any orientation, and nothing around you would tell you whether you were upside down or perfectly upright. Concepts that once seemed absolute begin dissolving almost immediately. Up and down become little more than habits your brain has carried from another world. It is a surprisingly uncomfortable realization. Human beings evolved beneath open skies, surrounded by landscapes that never stopped providing reference points. Our brains became extraordinarily skilled at navigating forests, rivers, mountains, and coastlines, but they were never designed to understand infinity. Even distance begins to lose its meaning. A nearby star may appear almost identical to another, located hundreds of times farther away. Without familiar objects for comparison, your eyes struggle to judge scale. Something that seems close enough to reach could actually be many trillions of miles away, while another object appearing no brighter might be unimaginably more distant still. The universe quietly refuses to behave according to everyday intuition. Then there is the silence. On Earth, silence usually means the absence of noticeable sounds. Perhaps you have experienced it while walking through fresh snow, standing alone beside a quiet lake at dawn, or sitting inside a peaceful library where every whisper feels unusually loud. But the silence of space is something entirely different. Sound is simply a vibration passing from one particle to another. Air carries it effortlessly around us every day. Water carries it even farther. But the immense emptiness between the stars contains almost nothing at all. There is simply no pathway for sound to travel. If you tried calling for help, your voice would never leave the small pocket of air surrounding you. Your words would fade before reaching anyone else. Even if another traveler floated only a short distance away by cosmic standards, the universe between you would remain perfectly silent. It is a strange thought. For perhaps the first time in your life, communication itself becomes impossible. Yet the greatest challenge may not be physical at all. It may be psychological. Human beings are profoundly social creatures. Throughout our history, survival depended upon families, communities, and shared experiences. Even today, many people find comfort simply knowing that someone else is nearby, even without speaking a single word. Now imagine knowing that no one is coming, not because they don't care, not because they cannot find you, but because the universe itself is simply too vast. The realization settles slowly rather than suddenly. There is no dramatic explosion, no terrifying roar, only an expanding awareness that your existence has become almost unimaginably small against the backdrop of cosmic space. Curiously, the universe is doing nothing to harm you. It isn't angry, it isn't cruel, it isn't even paying attention. And perhaps that quiet indifference feels stranger than hostility ever could. We often imagine danger as something with intention, a predator that hunts, a storm that approaches, an enemy that chooses to attack. But space behaves differently. It does not seek you out, it simply continues being exactly what it has always been, an endless expanse governed by patient physical laws. That quiet indifference can reshape the way we think about fear itself. Perhaps the most unsettling realization is not that the universe wants to destroy us. It is that our existence has never been necessary for its story to continue, long before the first. And yet, rather than making our lives meaningless, this perspective can also inspire a different kind of wonder. Against such staggering emptiness, every conversation shared with another person becomes remarkably precious. Every sunrise, every memory, every familiar landscape becomes something extraordinary precisely because it exists within a universe so overwhelmingly vast. Perhaps that is why astronauts often describe looking back at Earth as one of the most emotional experiences of their lives. Seen from enough distance, our planet no longer appears divided into countries or continents. It becomes a small, luminous home floating peacefully through an ocean of darkness, a tiny island of warmth surrounded by unimaginable space. For a while, the silence almost feels comforting again. The stars continue their patient glow, and the darkness no longer seems quite so threatening. But appearances in the universe can be wonderfully deceptive, because somewhere ahead, invisible to the eye at first, space itself begins to change. Not through sound, not through light, but through gravity, quietly bending the very fabric of reality itself. For a long time, gravity seems almost ordinary. It keeps your feet on the ground. It guides the moon around the Earth and the Earth around the sun. It quietly shapes the seasons, the tides, and the gentle rhythm of our days. Because it is always with us, gravity feels familiar, almost invisible. But familiarity can be deceptive. Imagine laying a heavy blanket across a soft mattress. At first, the blanket rests almost perfectly flat. Then you place a large stone at its center. The fabric sinks inward, creating a gentle curve. If you roll a small marble nearby, it no longer travels in a straight line. Instead, it follows the shape of the blanket itself. Gravity behaves in much the same way. Rather than reaching out like an invisible hand, massive objects reshape the very stage upon which everything moves. Planets, stars, light itself, all follow the curves woven into space and time. Most of the time, those curves are gentle. Around certain objects, however, they become unimaginably steep. A black hole begins with a star many times larger than our Sun. For millions of years, the star shines by balancing two enormous forces. Gravity constantly pulls inward, while energy from nuclear fusion pushes outward. For an astonishing span of time, these two forces remain almost perfectly balanced, like a dancer standing effortlessly on one foot. Eventually, the fuel runs out, the outward pressure fades. Gravity, having patiently waited all along, finally takes control. The star collapses under its own immense weight, shrinking farther and farther until it creates one of the strangest objects known to science, a black hole. Despite its name, a black hole is not truly a hole in the ordinary sense. It is better imagined as a region where the landscape of space has become so steep that every possible path leads inward. Even light, the fastest traveler in the universe, can no longer climb back out. Surrounding every black hole is an invisible boundary known as the event horizon. You might imagine it as the edge of a vast waterfall. Far upstream, the river flows gently. A skilled swimmer could easily make progress against the current. Closer to the edge, the water moves faster and faster until, at one particular point, the current becomes impossible to overcome. Beyond that point, every path leads over the falls. The event horizon works in a surprisingly similar way. Crossing it would not necessarily feel dramatic in that exact instant. There is no solid wall, no sudden flash of light, no cosmic alarm announcing your arrival. Yet once you pass beyond that invisible boundary, every future leads deeper inward. Returning is no longer part of the universe's possibilities. Something equally fascinating happens to time itself. Far from a black hole, clocks continue ticking as they always have. But near the event horizon, time slows dramatically when viewed from a safe distance. Imagine watching a friend slowly walk toward that invisible boundary. To you, their movements appear slower and slower, almost as though time itself has become thick like flowing honey. Eventually, they seem nearly frozen at the edge. Yet from your friend's own perspective, everything still feels perfectly normal. Their heartbeat continues, their thoughts continue, Their clock never notices anything unusual. The universe somehow allows two completely different experiences of time to exist at once. As extraordinary as this sounds, it has been confirmed again and again through Einstein's theory of relativity. The closer one approaches extreme gravity, the more differently time unfolds. Then comes one of the most famous and most unsettling ideas associated with black holes: spaghettification. The name sounds almost playful, but the reality behind it is anything but. Gravity grows stronger the closer you move toward the center of a black hole. If your feet are slightly nearer than your head, they experience a stronger pull. At first, the difference is tiny. Then it grows steadily larger, gently stretching your body until every part experiences gravity differently. Scientists gave this strange process an unexpectedly memorable name because objects would gradually become longer and thinner, rather like strands of pasta. It is one of those rare moments where science sounds almost whimsical while describing something profoundly extreme. Yet perhaps the deepest mystery lies beyond stretching or gravity. It concerns information itself. Every object carries information about what it is, its structure, its history, even the arrangement of its smallest particles. If something disappears into a black hole forever, what becomes of that information? Does it vanish? Can nature truly erase part of its own history? Or is the information somehow preserved in ways we have not yet learned to understand? For decades, some of the world's greatest physicists have wrestled with this question. It remains one of modern science's most fascinating puzzles. There is another remarkable idea that makes black holes even stranger. Although they seem eternal, they may not last forever. Over timescales so immense that they dwarf the current age of the universe, black holes are predicted to release tiny amounts of energy through a process known as Hawking radiation. Bit by bit, over unimaginable stretches of time, they slowly lose energy until even these seemingly immortal giants may eventually fade away. Nothing in the universe appears completely permanent. Yet nature has another surprise waiting. Sometimes a massive star does not collapse far enough to become a black hole. Instead, gravity compresses it into something almost equally astonishing: a neutron star. Imagine taking a mountain, a continent, or even an entire world, and patiently compressing it until almost all the empty space inside its atoms disappears. The result is matter, packed together so tightly that a single spoonful would outweigh anything our everyday experience can truly comprehend. It is no longer the kind of matter we encounter in ordinary life. It is matter transformed into one of nature's most extraordinary states. Many neutron stars spin with astonishing speed, completing hundreds of rotations in a single second. Some sweep beams of radiation across space like the steady light of a distant lighthouse, producing rhythmic signals that astronomers have detected for decades. Others become even more extreme. These are magnetars. Their magnetic fields are so powerful that they stretch far into surrounding space, influencing matter in ways that seem almost unbelievable. Rather than imagining enormous numbers, it is enough to picture a force so intense that it reshapes its surroundings long before anything ever touches its surface. Nature, it seems, has no shortage of imagination. Black holes reveal gravity carried almost to its ultimate conclusion. Neutron stars reveal matter compressed almost beyond recognition. Neither exists because the universe chose to frighten us. They exist because the same quiet physical laws that guide falling apples and orbiting planets continue working faithfully, even under conditions almost impossible to imagine. And as astonishing as these cosmic remnants may be, they are not the most violent events the universe can sum. Sometimes, instead of quietly bending space, the cosmos releases its energy in a single breathtaking flash, one so powerful that even an entire galaxy might briefly be outshone by its light. For all the strange wonders created by gravity, the universe occasionally reminds us that collapse is only one part of its story. Sometimes, instead of slowly bending space over millions of years, nature releases an astonishing amount of energy in a single moment. Imagine sitting beside a quiet campfire on a peaceful evening. The flames dance gently, warming the air around you. Everything feels calm and predictable. Now imagine that somewhere beyond the distant mountains, an entire forest suddenly erupts into light. You don't see every individual tree burning. You simply notice that the whole horizon has become brighter than it ever should be. A gamma-ray burst is something like that, but on a scale so immense that even this comparison barely hints at its true power. These extraordinary events occur when some of the largest stars in the universe reach the end of their lives, or when two neutron stars finally collide after slowly orbiting one another for millions of years. For an incredibly brief time, an enormous amount of energy is released. Not gently in every direction. Instead, much of that energy is concentrated into remarkably narrow beams, almost like two immense searchlights shining across the universe. This detail changes everything. If you happen to stand far away but outside those beams, you might never know the explosion occurred. Yet if a planet lies directly in their path, distance alone may offer surprisingly little protection. Fortunately, Earth appears to occupy a relatively safe neighborhood, and astronomers do not know of any nearby gamma-ray burst currently aimed in our direction. That is reassuring. But the phenomenon itself remains one of the clearest reminders that the universe can produce events far beyond anything our everyday experience prepares us to imagine. Unlike an approaching storm, there would be no dramatic warning visible in the sky, no growing sound, no slowly darkening clouds. The energy would already be traveling at the fastest speed the universe allows. By the time its light reached a distant world, the event itself would already belong to the past. Scientists believe that a sufficiently nearby gamma-ray burst could dramatically affect a planet's atmosphere. Rather than shattering mountains or splitting continents apart, it would quietly alter the invisible layers of gas surrounding the world. Those layers protect life every single day without asking for recognition. They soften harmful radiation from the sun. They help maintain temperatures suitable for oceans, forests, and living creatures. They are, in many ways, the invisible shield that allows Earth to remain a comfortable home. A powerful burst of high-energy radiation could weaken that protection. The consequences might unfold gradually rather than instantly. Sunlight that once nurtured life could become increasingly harmful. Entire ecosystems could begin changing, not because the ground beneath them had broken apart, but because the delicate balance above them had quietly shifted. There is something strangely unsettling about this possibility. The universe does not always destroy through dramatic explosions. Sometimes it changes only one small piece of a much larger system. Everything else follows naturally afterward. Yet even events as astonishing as gamma-ray bursts belong firmly within the world of observation. We have detected them. We have measured them. Although many details remain under investigation, they are unquestionably part of our universe. The next idea occupies a very different place. It belongs to the fascinating borderland where mathematics, imagination, and physics briefly walk together. Imagine standing beside a spring deep within a quiet forest. Fresh water flows endlessly outward. No matter how long you watch, nothing ever seems to flow back inside. The spring simply continues giving. Now imagine replacing water with light, energy, and matter itself. This gentle image offers one way to begin thinking about a white hole. If a black hole represents a region from which nothing can escape, a white hole is often described as its theoretical opposite. Nothing can enter. Everything can only emerge. At first, the idea sounds almost backwards. After all, nearly every process we observe in everyday life seems to move toward greater mixing and greater disorder. Rivers flow downhill, smoke drifts into the air, hot coffee gradually cools. Nature appears to favor one direction. White holes seem to suggest another. It is important to pause here for a moment. Unlike black holes, no white hole has ever been observed. No telescope has captured one. No spacecraft has detected one. They arise from certain mathematical solutions of Einstein's equations where the geometry of space and time allows such an object to exist under particular conditions. Whether nature actually creates them remains completely unknown. Even so, the idea continues to fascinate physicists. Some speculative models have explored whether white holes might be connected to wormholes, hypothetical tunnels linking distant regions of space, or whether they could represent an unusual stage in the life of a black hole. Others suggest they may never exist outside mathematics at all. For now, no one truly knows, and perhaps that uncertainty is part of their quiet beauty. Science is often imagined as a collection of definite answers. In reality, it is equally a discipline of carefully exploring unanswered questions. Some ideas become accepted, others are discarded. A few remain suspended in uncertainty for decades, patiently waiting for new evidence to reveal whether nature has chosen to make them real. White holes belong to that rare and intriguing category. They remind us that mathematics can sometimes lead human imagination farther than observation has yet traveled. Whether they exist or not, they encourage us to ask deeper questions about how the universe is constructed. Questions, after all, have always been the first step toward discovery. By now, the universe has revealed several different kinds of wonder. Some can compress stars into objects smaller than cities. Some can release more energy in seconds than our sun will produce during its entire lifetime. Others may exist only as elegant possibilities hidden within equations. And yet, despite everything we have explored so far, every one of these phenomena shares something important. They all involve objects we can point toward. Objects with locations. Objects that, at least in principle, belong somewhere within space. But the next mystery is far more unsettling, because it asks us to consider that most of the universe may not be invisible simply because it is too far away. It may be invisible because we have never truly understood what most of reality is made of. For thousands of years, human beings believed that seeing was the same as knowing. If something reflected light, cast a shadow, or left footprints in the sand, it could be understood. We built our earliest knowledge of the world through our senses. Even today, much of everyday life still depends upon that quiet assumption. You look outside your window and see trees swaying in the breeze. You watch rain fall from dark clouds. You see the moon rise above the horizon. Light carries stories from distant places, allowing your eyes to build a picture of the world around you. It feels complete. Yet the universe gently suggests something very different. Imagine walking into an enormous cathedral just after sunset. Only a handful of candles remain lit. Their warm glow reveals a few nearby pillars, perhaps a section of the floor, and part of the ceiling high above. Everything you can see feels real and familiar. But beyond that small circle of light stretches a vast interior still hidden by darkness. The walls are there, the arches are there, the great columns are still supporting the roof. You simply cannot see them yet. Modern astronomy has gradually revealed that our universe may be much like that cathedral. Everything that shines, every star, every glowing nebula, every planet, every galaxy you have ever seen in photographs, appears to make up only a small portion of the cosmos. The rest remains largely invisible. This realization did not arrive overnight. It emerged quietly, almost by accident. As astronomers carefully measured how galaxies rotate, they noticed something unexpected. The outer stars were moving much faster than they should have been. Imagine children riding a merry-go-round. The horses near the center move comfortably together, while those near the edge must travel much farther during each rotation. Now imagine the outer horses moving so quickly that they should simply fly away. Instead, they remain perfectly in place. Something unseen continues holding everything together. That invisible influence became known as dark matter. The name sounds mysterious, but in many ways it is simply an honest description. It is dark because it neither emits nor reflects light. It is matter because it behaves as though it possesses gravity. Beyond those observations, much remains uncertain. Scientists have searched for its true identity for decades. They have proposed possibilities. They have designed sensitive experiments. Yet the fundamental nature of dark matter remains one of modern astronomy's greatest unanswered questions. Although we cannot see it directly, we can watch what it does. Its gravity gently bends the paths of light, traveling across enormous distances. Sometimes a distant galaxy appears stretched into graceful arcs or delicate rings because invisible matter lies between it and us. It is rather like noticing the shape of a clear glass window only after sunlight begins bending through it. The glass itself is almost invisible. Its effects reveal its presence. On even larger scales, dark matter appears to weave an immense cosmic framework. Galaxies do not scatter randomly through space like grains of sand tossed into the wind. Instead, they gather along enormous filaments, forming a structure that resembles a vast network of rivers viewed from high above. Clusters connect to clusters. Great empty regions lie between them. The universe, despite its staggering size, possesses an unexpected architecture, and much of that hidden architecture appears to be shaped by something we still cannot identify. If that thought feels humbling, another discovery becomes even more surprising. For many years, astronomers assumed that gravity should gradually slow the expansion of the universe. After all, gravity pulls things together. That seemed perfectly reasonable. Imagine tossing a ball into the air. It rises for a while, then gravity gently slows it until, eventually, it begins falling back toward your hand. The expanding universe was expected to behave in much the same way. Instead, careful observations revealed exactly the opposite. The expansion is speeding up. Galaxies are drifting away from one another faster today than they were billions of years ago. Something appears to be encouraging space itself to grow ever more rapidly. That mysterious influence became known as dark energy. The name, once again, reflects honesty more than certainty. We know remarkably little about its true nature. We know only what it seems to accomplish. Imagine baking a loaf of raisin bread. As the dough slowly rises inside the oven, every raisin moves farther from every other raisin. No single raisin is actively traveling across the dough. Instead, the dough itself is expanding. The universe behaves in a surprisingly similar way. Galaxies are not simply racing through empty space. Space itself is quietly stretching between them. For countless generations, this expansion changed almost imperceptibly. But over immense cosmic timescales, even tiny differences become profound. One day, astronomers in distant civilizations may look into the night sky and find far fewer galaxies than we can see today. Not because those galaxies disappeared, not because their stars stopped shining, but because the expanding universe carried them so far away that their light could never reach them again. This remarkable boundary is sometimes called the cosmic event horizon. Unlike the event horizon surrounding a black hole, it does not trap objects through overwhelming gravity. Instead, it quietly marks the limit beyond which the continuing expansion of space forever separates distant regions of the universe from our own. It is a gentle kind of disappearance. Nothing dramatic occurs. The galaxies simply fade from view over unimaginable spans of time, leaving every civilization with a progressively smaller window onto the cosmos. There is something quietly moving about this idea. We often imagine knowledge as something that continually grows. Yet the universe reminds us that opportunities can also slowly drift away. Future astronomers may never know how richly populated the universe once appeared. Their skies could become lonelier than ours. By now, a remarkable pattern has begun to emerge. Black holes taught us that gravity can become almost unimaginably powerful. Gamma-ray bursts revealed that nature can release astonishing amounts of energy. Dark matter reminds us that most of the universe cannot be seen. Dark energy suggests that space itself is still changing. The more carefully we observe reality, the more it seems to extend beyond ordinary intuition. And perhaps the most unsettling possibility still waits quietly beneath all of these discoveries. Because everything we have explored so far has assumed one comforting idea: that the laws of physics themselves remain constant, that the universe, however mysterious, follows the same fundamental rules everywhere and everywhen. But what if even that quiet certainty turns out to be only temporary? Until now, every mystery we've explored has shared something reassuring. Black holes may bend space beyond recognition. Neutron stars may compress matter into forms unlike anything on Earth. Gamma-ray bursts may unleash extraordinary amounts of energy. Dark matter and dark energy may shape the destiny of galaxies while remaining almost completely invisible. Yet beneath all of those discoveries lies one comforting assumption: the universe itself is stable. Its laws remain dependable. Gravity behaves today as it did billions of years ago. Light still travels in the same way. Atoms still gather together to build stars, oceans, mountains, and living creatures. Everything we know depends upon that quiet consistency. But what if the universe has been balancing on something far less permanent than we imagine? Imagine walking across a beautiful frozen lake during the middle of winter. The ice beneath your feet feels perfectly solid. Each step brings confidence. The surface stretches peacefully toward the distant shoreline, smooth and unbroken beneath the morning light. You have every reason to believe the lake is exactly what it appears to be. Then someone quietly tells you something unexpected. The ice supporting you is not the thickest layer. Far below, hidden beneath the surface, lies an even deeper level where the water has frozen into something stronger and more stable. Suddenly, the same peaceful landscape feels very different. Nothing has changed. The lake still looks exactly as it did a moment ago, yet your understanding of it has. Modern physics entertains a remarkably similar possibility. According to one theoretical idea, the universe we experience may not occupy its most stable state after all. Instead, it could exist within what physicists call a false vacuum. Despite its name, this has nothing to do with empty space as we usually imagine it. Even what we call empty space is not truly empty. Invisible fields quietly fill every corner of the universe. Among them is one particularly important field known as the Higgs field. You might picture it as an invisible landscape stretching across all of reality. Every particle moves through this landscape continuously, much as fish move through water without ever noticing the ocean surrounding them. The Higgs field quietly helps determine one of the most fundamental properties in nature: mass. Without it, the universe would look unimaginably different. Stars might never form, planets might never gather. Life, as we understand it, might never have emerged. For decades, scientists suspected that this invisible field existed. Then, after years of remarkable engineering and international collaboration, experiments finally confirmed the existence of its associated particle, providing one of the great scientific achievements of the modern age. Yet confirmation also opened another fascinating question. What if the Higgs field is not resting in its deepest possible state? Imagine placing a marble inside a shallow valley. From nearby, the marble appears perfectly still. It has stopped moving. Everything seems stable. But far beyond the surrounding hills lies another valley, much deeper than the first. The marble has not reached the lowest point after all. It has merely become temporarily comfortable. Most of the time, that would not matter. The marble could remain exactly where it is for an unimaginably long time, perhaps longer than the current age of the universe itself. Yet quantum physics occasionally behaves in ways that differ from everyday experience. On the smallest scales, particles sometimes accomplish things that seem impossible from a classical point of view. One of these remarkable behaviors is called quantum tunneling. Rather than climbing over a hill in the ordinary sense, nature occasionally allows extraordinarily unlikely transitions to occur without following the path our intuition expects. The probability is astonishingly small, so small that many physicists suspect such an event may never happen throughout the lifetime of our observable universe. And yet, the probability is not necessarily zero. If such a transition were ever to occur, a tiny region of space could suddenly settle into that deeper state. At first, it might be no larger than an unimaginably small point, almost insignificant, almost invisible. But this new region would not remain small. It would begin expanding, not because something exploded, not because enormous pressure pushed it outward. It would simply represent a more stable version of reality, gradually replacing the older one. The expanding boundary is often described as a bubble. That word can sound strangely gentle, almost playful, but appearances can be misleading. Unlike an ordinary soap bubble drifting through the air, this boundary would move at the fastest speed information itself can travel. Nothing could outrun it. Nothing could send a warning ahead. Imagine reading a letter whose final sentence disappears before your eyes. Imagine watching a sunrise that quietly changes the meaning of light itself. These images still fall far short of the actual idea, because vacuum decay is not merely the destruction of objects. It is the transformation of the rules those objects obey. Atoms might no longer remain stable. Chemical reactions could become impossible. The forces that bind matter together might no longer behave as they once did. The universe would not simply lose its familiar appearance. It would become governed by an entirely different set of physical conditions. Perhaps the most unsettling aspect of this possibility is its silence. There would be no distant rumble announcing its arrival, no growing wall of fire crossing the stars, no dramatic countdown. If such an event were ever to begin somewhere beyond our view, the light carrying that information would travel no faster than the boundary itself. By the moment anyone could observe it, the transformation would already have arrived. Fortunately, it is important to remember that this remains a theoretical scenario. Modern physics does not predict that vacuum decay is about to happen, nor do observations suggest any immediate reason for concern. Instead, the idea serves as a profound reminder of how deeply scientists continue questioning even the most fundamental assumptions about reality. The universe invites curiosity, and sometimes curiosity leads us toward possibilities that are both beautiful and deeply humbling. It reminds us that certainty is often more fragile than it first appears. Yet even this extraordinary idea assumes one quiet constant: that there is someone present to wonder about it, someone observing, someone remembering, someone asking questions. But what if the greatest mystery has never been the universe around us? What if the deepest uncertainty lies within the observer itself? For almost our entire journey, the questions have been directed outward. We have looked toward distant stars, invisible matter, collapsing suns, and even the possibility that the laws of physics themselves might someday change. No matter how strange those ideas became, one assumption quietly remained beside us. You were the observer, the universe was the mystery. But every so often, science has a remarkable way of turning the telescope around. Instead of asking what is happening out there, it gently asks a far more personal question. What if the greatest mystery has been the one doing the observing all along? Imagine waking up tomorrow morning. The sunlight slips through the curtains just as it always has. You recognize your bedroom. You remember your childhood, your family, perhaps the first book you ever loved, or the place where you learned to ride a bicycle. Everything feels perfectly familiar. Nothing seems unusual. Now imagine that every one of those memories appeared only an instant ago. Not because someone erased your past, not because you forgot anything, but because there never was a past to begin with. It sounds almost impossible, and perhaps that is exactly why the idea has fascinated physicists and philosophers for generations. To understand where it comes from, we first need to think about something surprisingly ordinary. Imagine leaving a carefully built sandcastle alone on a windy beach. Given enough time, the wind and waves will gradually soften its walls until the castle disappears into countless grains of sand. That feels natural. Order slowly becomes disorder. Now imagine the opposite. Imagine every grain of sand suddenly gathering itself together to rebuild the castle exactly as it was before. The towers return. The windows reappear. Every tiny detail finds its proper place without anyone touching it. You would almost certainly call it impossible. Yet from the viewpoint of physics, it is not completely impossible. It is simply so unimaginably unlikely that you would never expect to witness it during the lifetime of the universe. Nature usually moves toward greater disorder. Physicists describe this overall tendency using a concept called entropy. You don't need complicated equations to understand it. A tidy room naturally becomes untidy unless someone continues arranging it. A drop of cream quickly mixes into a cup of coffee, but the coffee never quietly separates itself back into cream and coffee again. Broken leaves scatter across a garden path. They never gather themselves neatly into a tree. The universe displays this quiet preference almost everywhere we look. Yet probability is a curious thing. Given enough time and enough opportunities, even extraordinarily unlikely arrangements become possible. This realization inspired one of the strangest thought experiments in modern cosmology. Imagine a universe so unimaginably old that almost every star has faded away. Almost nothing changes anymore. For endless ages, tiny random fluctuations continue occurring within the quiet background of reality. Most of them are insignificant, but given enough time, far longer than any number we ordinarily imagine, could an extraordinarily complex arrangement briefly appear entirely by chance. Not an entire planet, not an entire civilization, just one conscious brain, complete with memories, thoughts, emotions, a sense of identity. Such a hypothetical observer became known as a Boltzmann brain, named after the physicist Ludwig Boltzmann, whose work helped shape our modern understanding of entropy. The idea is not presented because scientists believe invisible brains are quietly floating through space. Quite the opposite. It exists as a philosophical puzzle, a way of testing whether certain cosmological theories make logical sense. Because if a theory predicts that randomly formed observers would eventually become more common than ordinary observers like us, then perhaps something about the theory itself requires rethinking. Still, even as a thought experiment, the idea carries an unusual emotional weight. Imagine closing your eyes tonight. When you wake tomorrow, how do you know your memories truly belong to a continuous life? How do you know yesterday genuinely happened? Most of us answer immediately, because we remember it, because other people remember it too, because photographs, books, and history all seem to agree. And in everyday life, those answers are entirely reasonable. Yet the Boltzmann brain thought experiment quietly points towards something deeper. Every piece of evidence you possess ultimately arrives through your own conscious experience. Your memories, your senses, your thoughts. Those same tools are also the things being questioned. It creates a remarkable philosophical circle, not one intended to undermine reality, but one that reminds us how extraordinary consciousness truly is. After all, consciousness remains one of science's greatest mysteries, We understand neurons. We understand electrical signals. We understand many of the remarkable processes occurring inside the brain. Yet the simple experience of being aware, the feeling of existing in this moment, continues to resist complete explanation. Perhaps that is why ideas like the Boltzmann brain linger in scientific conversations, not because they are likely, but because they encourage us to examine assumptions we rarely notice ourselves making. Fortunately, modern cosmology offers many reasons to believe our universe developed through a rich and continuous history, rather than through isolated random fluctuations. The galaxies surrounding us, the cosmic background radiation left behind by the early universe, the remarkable consistency of physical observations across immense distances. All of these provide strong evidence that we inhabit a universe with a genuine past stretching back nearly 14 billion years. That should be reassuring. And yet, the thought experiment leaves behind a quiet gift. It reminds us not to take consciousness for granted. Every memory, every conversation, every moment of curiosity, every glimpse of the night sky, each depends upon something far more remarkable than we usually pause to appreciate. The simple fact that we are here to experience them at all. As strange as this journey has become, it is worth remembering that our own awareness has been traveling alongside every discovery. Without conscious observers, black holes would remain unnamed, stars would shine unnoticed, galaxies would continue their silent dance without anyone wondering where they were going. And speaking of movement, our own galaxy has been traveling as well. Not wandering aimlessly through space, but drifting, together with countless neighboring galaxies, toward an enormous destination that remained hidden for millions of years before humanity finally noticed its quiet gravitational pull. If you step outside on a clear evening and look up at the stars, everything appears wonderfully still. The familiar constellations hold their places night after night. The Milky Way stretches quietly across the darkness like a faint river of light. The sky feels timeless, almost motionless, as though the universe itself has settled into a peaceful silence. But appearances can be wonderfully deceptive. Imagine standing aboard a large ship crossing a calm ocean. If the sea is smooth and the horizon remains steady, you might feel perfectly still. You could place a cup of tea on a table, watch the gentle ripples on its surface, and believe nothing is moving at all. Only later do you realize the ship has been traveling hundreds of miles while you were quietly enjoying the journey. Our home in the universe is rather like that. The Earth circles the Sun. The Sun orbits the center of the Milky Way. The Milky Way travels together with dozens of neighboring galaxies in what astronomers call the local group. For a long time, this seemed like a satisfying picture, a galaxy moving through space, surrounded by a small family of companions. Then, measurements became more precise. Astronomers noticed something unexpected. Our entire local group was drifting through space in a particular direction, not slowly, not randomly, but with remarkable purpose. It was as though every nearby galaxy had quietly joined the same invisible current. Imagine watching autumn leaves floating across a wide lake. At first, each leaf seems to wander independently. Then you notice something subtle. No matter where the leaves begin, they all drift toward the same distant corner of the water. The leaves themselves are not communicating. They are simply responding to a current hidden beneath the surface. The galaxies appeared to be doing something remarkably similar. Something enormous seemed to be pulling them all in the same general direction. Yet no one could see exactly what that something was. This mysterious region became known as the Great Attractor. The name sounds dramatic, almost like the title of a science fiction novel. In reality, it describes one of astronomy's most fascinating observations. The Great Attractor is not believed to be a single gigantic object waiting in the darkness. Instead, it appears to be a vast region containing extraordinary amounts of matter, including countless galaxies gathered together across unimaginably large distances. Its gravity quietly influences everything around it. Even our own galaxy participates in that immense gravitational dance. One question naturally follows. If something so enormous exists, why can't we simply point a telescope toward it? The answer brings us back to a familiar experience. Imagine trying to admire a distant mountain while standing inside a dense forest. The mountain has not disappeared, it is still there, but nearby trees block your view. You know something lies beyond them, yet the closer obstacles prevent you from seeing the full landscape. Astronomers face a surprisingly similar challenge. Our solar system sits inside the broad disk of the Milky Way. When we look towards certain parts of the sky, billions of nearby stars, enormous clouds of gas, and countless particles of cosmic dust fill our view. Together, they create a kind of natural curtain. This region is often called the zone of avoidance. Not because astronomers wish to avoid it, but because the dense material within our own galaxy makes observations extremely difficult. It is rather like trying to study a distant city through a thick morning fog. Little by little, new instruments have begun seeing through that cosmic curtain. Radio telescopes, infrared observations, and other techniques have gradually revealed more of the hidden universe. The picture continues to improve, yet even today, many questions remain. The Great Attractor itself appears to be only part of something even larger. Astronomers now recognize that our galaxy belongs to an immense collection known as the Laniakea supercluster. Its name comes from the Hawaiian language and is often translated as immeasurable heaven. It is a beautiful description. Within this enormous cosmic neighborhood, hundreds of thousands of galaxies slowly drift together, guided by gravity across distances so vast that ordinary numbers begin to lose their meaning. Standing inside such a structure is rather like standing within a single valley while trying to understand an entire continent. The farther our perspective expands, the more connections we discover, and perhaps those connections do not end there. Some astronomers suspect that even larger structures may continue beyond the regions we have already mapped. Clusters join superclusters, filaments stretch across unimaginable distances. Enormous empty regions separate them like quiet cosmic oceans. The universe begins to resemble a living tapestry woven from threads of galaxies, each responding to invisible patterns created billions of years ago. There is something wonderfully humbling about this image. For much of human history, we imagined ourselves standing at the center of everything. Then we learned that Earth circles the Sun. Later we discovered the Sun is only one ordinary star among hundreds of billions. Then we realized our entire galaxy belongs to an even greater family. And now we find that this family itself is gently flowing along currents so vast that we have only recently begun to recognize them. Each discovery has quietly expanded our sense of place, not by making humanity less important, but by revealing that reality is far richer than we once imagined. Perhaps that is one of science's greatest gifts. Every answer gently opens the door to another question. The Great Attractor reminds us that there are still landscapes hidden beyond our current maps. Invisible rivers of gravity continue carrying galaxies through space, patiently shaping the architecture of the cosmos. Yet even these magnificent structures are not eternal. Gravity gathers, stars shine, galaxies travel, but time continues its silent work upon them all. Eventually, every current reaches a future that none of them can avoid. And so our journey arrives at its final question. Not where the universe is going, but what becomes of the universe itself. When we first began this journey, the universe felt unimaginably vast. You floated alone in a silent ocean without a horizon. You watched gravity fold space around black holes, witnessed stars collapse into objects denser than imagination, followed invisible matter shaping entire galaxies, and considered the astonishing possibility that reality itself might someday change. Now, only one question remains. What happens when the universe finally reaches the end of its own story? For most of human history, people imagined the universe as something permanent. The stars seemed eternal. The night sky appeared unchanged from one generation to the next. Even though civilizations rose and fell beneath those familiar constellations, the heavens themselves felt timeless. Modern astronomy has revealed something far more remarkable. The universe has a history. It had a beginning. It has been changing for billions of years. And one day, it will almost certainly be different again. One of the most widely discussed possibilities is known as heat death. Despite its dramatic name, this ending is not fiery at all. In fact, it is defined by the gradual absence of change. Imagine placing a cup of hot tea on a quiet table. At first, steam rises gently into the cool air. Minute by minute, the tea becomes a little less warm. Eventually, it reaches the same temperature as the room around it. Nothing dramatic happens. The tea does not explode. It simply loses the difference that once made it special. The universe appears to behave in a surprisingly similar way. Stars shine because differences exist. One region is hotter than another. One place contains more energy than another. Those differences allow light to travel, planets to form, and life to emerge. But over unimaginable stretches of time, those differences slowly fade. One by one, the stars exhaust the fuel that has illuminated them for billions of years. Some quietly become white dwarfs, slowly cooling in the darkness. Others collapse into neutron stars or black holes. Eventually, new stars become increasingly rare. The night sky grows darker. Galaxies drift farther apart, until each becomes an island, surrounded by distances so immense that no neighboring galaxies remain visible. Imagine living in a small village surrounded by mountains. Over many centuries, the roads gradually disappear beneath forests. Bridges slowly crumble. The paths connecting one community to another quietly vanish. The villages still exist, but each one becomes more isolated than the last. Something similar happens on a cosmic scale. The universe does not suddenly become empty. It simply becomes increasingly lonely. Even black holes, those extraordinary objects that once seemed almost eternal, may not remain forever. Earlier, we briefly encountered the remarkable idea of Hawking radiation. Although the process is unimaginably slow, black holes are expected to release tiny amounts of energy over extraordinary spans of time, patiently, silently, almost imperceptibly. Eventually, after lengths of time so vast that ordinary language struggles to describe them, even the last black holes may disappear. By then, the universe would be unimaginably dark, remarkably quiet, a place where almost nothing new ever happens again. This is heat death, not an ending filled with violence, but one defined by stillness. Yet nature sometimes reminds us that certainty is a luxury science rarely claims. There is another possibility, one far more dramatic. Throughout our journey, dark energy has quietly remained in the background, gently encouraging the universe to expand. So far, observations suggest this expansion is accelerating. But suppose that acceleration never slows. Suppose it gradually becomes stronger, stronger still. Imagine holding a loosely woven piece of fabric. At first, you pull gently from opposite sides. The threads stretch only slightly. Nothing breaks. Now imagine pulling a little harder. The fabric begins to strain. Eventually, individual threads snap one by one until the entire cloth comes apart. Some cosmological models imagine a similar future for the universe. This scenario is known as the Big Rip. In this picture, the expansion of space eventually becomes so powerful that gravity can no longer hold galaxies together. Galaxy clusters slowly separate, then individual galaxies begin to unravel, Much later, even solar systems may lose their delicate balance. Planets drift away from their stars. Moons leave their planets. The familiar architecture of the cosmos gradually dissolves. If the expansion continued growing stronger still, the consequences would become even more extraordinary. The forces holding matter together might eventually be overcome. Atoms themselves could no longer remain intact. The universe would not merely become empty, its very structure would slowly come apart. Fortunately, this remains only one possible future among several that scientists continue to investigate. Current observations do not tell us with complete certainty which ending nature has chosen, and perhaps that uncertainty carries its own quiet beauty. Science is not simply the collection of answers. It is also the patient acceptance of questions that have not yet reached their conclusion. As our journey begins to draw to a close, it is worth remembering where we started. At the beginning of the night, you imagined yourself floating alone beneath an endless sky. That silence once felt frightening. Now it feels different, not because the universe has become smaller, not because its mysteries have disappeared, but because familiarity has quietly replaced uncertainty. The black holes remain. Dark matter still surrounds the galaxies. The Great Attractor continues its invisible work. The future of the cosmos is no less mysterious than it was an hour ago. And yet understanding has a remarkable way of softening fear. The unknown does not always become less extraordinary once it is explained. Sometimes it becomes even more beautiful. Perhaps that is one of science's quietest gifts. It does not promise certainty. It does not promise comfort. Instead, it offers perspective. The stars above us are not distant decorations scattered across the night. They are chapters in an ancient story that began billions of years before humanity first looked upward with wondering eyes. Every atom within your body was forged inside long-vanished stars. Every breath you take belongs to a universe that has been patiently evolving for almost 14 billion years. In a sense, you have never truly been separate from it. You have always been one small part of its unfolding story. And perhaps that is the gentlest thought to carry with you into the quiet hours ahead. The universe is unimaginably vast. It is filled with mysteries that may never be completely solved. Some inspire awe, some inspire humility, some remind us how little we still know, but all of them invite the same quiet response: to keep wondering, to keep looking upward, and to appreciate the extraordinary privilege of existing in a universe capable of asking questions about itself. So, as the stars continue their slow and timeless journey across the darkness, allow your own thoughts to grow a little quieter. Let the immense distances fade gently into the background. Let the mysteries rest where they belong, among the galaxies. And as sleep gradually finds you, remember that somewhere above, the universe continues its patient story, silent, beautiful, and endlessly unfolding. Good night.